Okay, in this lecture, we're going to continue with our section 2.5 material on physical applications of the integral. And in this lecture, we're going to be focused on what I call fluid pumping problems. The question of interest for our problems in this lecture will be if we have some tank that's filled with liquid, how much work would it take to pump that liquid out of the tank, or perhaps to a level above the tank through some pipe. So here we're still interested in the question of finding the work required to accomplish some task. And here the task we're referring to is pumping fluid out from a tank. So as a typical example problem to introduce how this will work, let's look at the following. We have an aquarium which is 6 meters long, 3 meters wide, and 2 meters deep, and it's full of water. So we're asked to find the work required to pump all of this water out of the aquarium. And so here when we're saying out of the aquarium, we're saying like over the top edge of this aquarium. And a little bit of information that we're given that we need for our problem is the weight density of water, which is given as the product rho times g, where rho is the density of water in kilograms per cubic meter. And then we would multiply by the acceleration due to gravity, g, which we are using a value of 9.8. And that product gives us 9,800, which is then in newtons per cubic meter. So to see how this problem will work, let's start by illustrating this. So we have an aquarium, 6 meters long, 3 meters wide, and 2 meters deep. So 3 meters along the bottom, 2 meters deep, and 6 meters long. And it's completely filled with water, we're told. We want the work required to pump this water out of the aquarium. So our method for finding this force or work required to pump fluid out of a tank is the same technique that we've been using throughout this section 2.5, which will be to think about taking our water in this tank and slicing it up into little slabs or slices. So let me think about taking a slice through this tank of fluid. So here I'm going to get a little slab of water, and the thickness of this slice I'll refer to as dx, so dx meters. And this slice I'm going to take at a distance of x meters from the bottom of my tank. So the question is, how much work would be required to lift or to pump this one slab of liquid to the top edge or just over the top edge of our tank? So to find the work required to do that, we need a couple of things. We need the force needed to move this slab of liquid and the total distance that it will travel to get to the top of our tank. So to clean up my figure a little bit here, let me maybe move where I've got this 2 meter depth. So it's 2 meters deep. So if my slice was taken at a distance of x meters from the bottom of the tank, the distance that this slab will have to move to get to the top of the tank would be 2 minus x meters. So that's the distance that this slab will have to travel to get to the top of our tank or be pumped out of this tank. And the other question that we need to address is what is the force needed to move that slab of liquid. Now what we're given here is the weight density of water. So it's 9,800 newtons per cubic meter. So to get the force needed to move that slab in newtons, I would need to determine the volume of this slab in cubic meters. Now we can see from our illustration here that our slab, or this slice of liquid, is a little rectangular prism, which is 6 meters long, the same as the length of our tank, 3 meters wide, same as the width of our tank, and then dx meters in depth or in thickness. So we can find the volume of our slice here. Let's start there. We'll say the volume of our slice is what I would call dV, a differential of the total volume of fluid in our tank. And it's given by a length, which was 6 meters, by width, which was 3 meters, by height or by depth, which was dx meters. So we have a volume of 18 dx cubic meters. So once I have the volume of my slice in cubic meters, I could multiply by its weight density to get the weight of this slab or the force needed to move this slab. So here I'll say the force needed to lift my slab or my slice of fluid is a differential of the total force, F, I need to pump all of the fluid out of this tank. And it would be found by taking my weight density of water, which is 9,800 newtons per cubic meter. We were given that in the problem. And then we multiply by its volume, which was 18 dx cubic meters. So we're left with 9,800 times 18, whatever this works out to, dx newtons. So in order to determine the work needed to lift this slice to the top of the tank, we would take the force needed to lift the slice and multiply by the distance it has to travel, which is our 2 minus x meters from the depth at which we took our, or the height at which we took our slice to get to the top edge of the tank. So here I'll say the work needed to lift this slice would be given by the differential of the total work done in pumping all of the fluid out of our tank. And it's found by taking the force needed to move our slice, which was 9,800 times 18 dx newtons. And multiplying by the distance this object travels, which is 2 minus x meters. So rewriting this just a bit, well, we have 9,800 times our 18 times the 2 minus x, if we distribute, would be 36 minus 18x. And then we have dx, where this is now measured in Newton meters or joules. So once we have the work needed to lift one slice to get the total work to pump all of the fluid to the top of the tank, we would add up the work for all of these slices by taking a definite integral of this work function, 9,800 times 36 minus 18x dx, where x could range from 0, if I'm taking a slice at the bottom edge of my tank, up to a height of 2 meters, since that was the depth of our tank here. So we're adding up these slices from x equals 0 to 2. So let's see what we have here. We can start by factoring out the 9,800 in front of our integral, and then finding the antiderivative of this function. We would have a 36x minus 9x squared, which is being evaluated from 0 to 2. So we have 9,800 times, when we evaluate at 2, 36 times 2 would be 72, minus 9 times 2 squared would be 36, and then we subtract what we get when we evaluate at x equals 0, which would be 0 here. So we are left with 9,800 times 72 minus 36, which would be 36. So let's see what this leaves us. 9,800 times this 36 would give us 352,800, where this is being measured in joules. Okay. So let's look at another problem. In this next example, we are asking a similar problem. We have a tank which has the shape of an inverted circular cone with a height of 10 meters and a base radius of 4 meters. And this tank is filled with water to a depth of 8 meters. So we're asked to find the work required to pump all of this water to the top of the tank, or just over the top edge, perhaps. So let's start by visualizing our tank. Here, our tank has the shape of an inverted circular cone. So it looks something like this. And we're told that the height of this cone was 10 meters. And it had a base radius, so the radius of our circle here at the base of our cone was 4 meters. And we're told that this tank is filled with water, not completely, but to a depth of 8 meters. So we're asked, what is the work required to pump all of this water to the top of our tank? So as we did with our previous example, let's consider taking a slice or a slab of our water at a depth or at a distance of x meters from the bottom of this tank. And we're curious, and let's call the depth of this slab dx, and we want to calculate the work required to lift that one slice to the top of the tank. And if we can find that, then we can determine how much work is required to pump all of this fluid to the top of the tank. So here, looking at our figure, we can see that this slice, if we take this out, would be a little disc shape. We have a circular conical tank, so if I take a slice through that tank, I would get a little disc shape of water of a thin width dx. And to find the volume of this slice, I would take the area of this disk, which would be pi r squared, and then multiply by its thickness dx. So the radius for this little slab, let me call r, and of course it depends on x. So the larger I take the value of x, the further I move up from the bottom of the tank, the radius of this disk will get larger. But let me call that r of x here. So in order to find the volume of this slab or this slice, I need to know what is r in terms of x. And in order to find it, I'm going to make use of similar triangles. So I can see here, if we were to think about dropping a little vertical line down through the center of my cone, I see that the triangle, which would be formed by that line and the outer edge of my cone, would have the same angle measures as the smaller triangle formed by taking, maybe use a different color here, formed by that vertical along with the outer edge of my tank and the top edge of my little slice of water. So if those two triangles have the same angle measures, they're said to be similar triangles. So a little scratch work here, I can say using similar triangles, the ratio of the base to the height of my larger triangle, which I had shown in green, it had a base of 4 meters and a height of 10 meters. And that ratio of the base to the height for my larger triangle must be the same ratio for the smaller triangle since they're similar triangles. That is, they have the same angle measures. So the base for my smaller triangle was this r of x function, my radius, and the height of that little triangle is what we were calling x, the distance from the bottom of the tank up to our slab. So solving for r of x, we would have 4/10, which is the same as 2/5, times x. So let's see what the volume of our little slab of liquid is. So here, the volume of our slice is dV. So the volume of this little disk shape would be given by the area of our base, which was the circle, pi r of x squared. So here we would have 2/5 x, we're squaring that radius, and then we multiply by the thickness of our slab, dx, and since everything was being measured in meters, the volume would then be cubic meters. Or simplifying a little bit, when we square the 2/5, that would be 4/25 times the pi out in front, would be 4/25 pi. Then squaring the x term, we have x squared and then dx cubic meters. Now, once we find the volume of our slab, we would multiply by the weight density of water in order to get the force needed to move that slab. So here, let me say the force needed to lift this slab, or my slice of liquid, is dF, which would be found by taking the weight density of water, which in our last example was given as 9,800 newtons per cubic meter, and we're multiplying by this volume, 4 pi over 25, x squared dx, cubic meters. So let's see what this gives us. So here, taking 9,800 and dividing through by a factor of 25, and then multiplying by 4 pi, we have our constants simplifying to 1,568 pi with an x squared dx, and this is now measured in newtons. So what I was doing here, I took the 9,800 times 4 pi over 25, that left me with this 1,568 pi, and then I still had my x squared dx. So once I have the force needed to lift this slice to get the work needed to lift this slice, well, we have to multiply by the distance that our slice travels. So if the height of our conical tank was 10 meters, and I took my slice at a distance of x meters from the bottom of the tank, then the distance from my slice to the top of the tank would be 10 minus x meters. So I can say the work needed, or the work done, in lifting the slice would be given by dW, which is found by taking my force, which was 1568 pi, x squared dx newtons, and multiplying by the distance traveled, which is 10 minus x meters. So our unit would then be Newton meters or joules. Or if we distribute this x squared term, we have 1568 pi times 10x squared minus x cubed dx joules. So once I have the work required to lift this one slice to the top of the tank, I can use a definite integral to sum the work required for each of these slices to get the total work required to pump all of the fluid to the top of the tank. So here, the work that I want to calculate is found by integrating this function. So of course I can pull the 1568 pi out in front, and I'm integrating this 10x squared minus x cubed dx. And let's think about our range of x values. So here, x was the distance from the bottom of the tank up to where I was taking my slice. So at the bottom edge of our tank, x would be 0, and then the height of the water goes to a depth of 8 meters. So at this top edge of the water, x would be 8. So I'm going to integrate from x equals 0 to 8 here. So let's see what we get. We have the 1568 pi times the antiderivative of this function would be 10/3 x cubed minus 1/4 x to the 4th. And we're evaluating from 0 to 8 here. So we have 1568 pi times a 10/3 times 8 cubed minus 1/4 times 8 to the 4th. And using a calculator to simplify here, we can find that this work would be approximately, let's see, this works out to 1.0704 times 10 to the 6th Newton meters or joules. So in that last step, it's probably helpful to make use of a calculator to simplify that arithmetic. And if we round this value, so if we don't want to express this in terms of pi, but if we want to get an approximate value, we could round this, and we find that this work is approximately the 1.0704 times 10 to the 6th joules, or approximately 1.07 million joules. So let's look at some other examples. In this next one, we're told that we have an 8-foot tank which is filled with water, and the ends of this tank are shaped like semicircles with a 4-foot diameter. And we are asked here to set up an integral to find the work required to pump this water through a 1-foot spout on top of the tank, but do not evaluate that integral. Now here, our problem is a little bit different in terms of measurement from what we've been considering. In our previous two examples, we were measuring everything in meters. Here we're measuring in feet. So in that case, the weight density of water is rho times g, which would be 62.4 pounds per cubic foot. So we're no longer using newtons per cubic meter, but in terms of pounds per cubic foot, the weight density of water is 62.4. So let's illustrate this again. We have a 8-foot long tank which is filled with water, and the ends are shaped like semicircles. So let's visualize this. We have a little semicircular end to our tank, which is 8 feet long. And we're told that it had the ends of the tank were semicircles with a 4-foot diameter, so 4 feet across this top. And then here we're taking this water and pumping it through a 1-foot spout on top of the tank. So we can think about on the top edge of our tank here, we might have a little spout, which we're told was 1 foot in height. So here we're told this tank was filled with water, so the water level is right along the top edge here. And the question is, how much work is required to pump all of this fluid through that 1-foot spout, or essentially pumping it to a height of 1 foot above the top edge of our tank? So our method is the same here. If we think about taking a slice of water through our trough of a small thickness dx feet, we need to determine the work needed to lift that slab or to pump it through the 1-foot spout, or lift it to a height of 1 foot above the edge of our tank. So in order to do that, I first need to determine the volume of this slab. So here, well, I can see if I take a slab through this tank, I'm going to get a little rectangular prism. And to find the volume, well, it's an 8-foot long tank, so it's going to be 8 feet in length, and then dx feet in thickness, but I need to know what is the length of this slab. Let me call it L of x, the length across this. And here I'm going to let x denote the distance from the top edge of my tank downward. So I'm using a slightly different notation in this problem. In the previous examples, I took x to be the distance from the bottom of the tank upward. For simplicity here, just notational simplicity, I'm going to take x to be the distance from the top of my tank down to the slab. And you can use either approach for any of these problems. You can use x as the distance from the top of the tank downward or from the bottom of the tank upward. So let's consider how we can find L of x. Of course, I see here the larger that I take the value of x, the smaller that the length of my strip becomes. So to find the length of this strip, I'm going to make use of the Pythagorean theorem. Let's think about how to generate a triangle here. So if I consider the distance from the center of this circle to the outer edge of my tank, well, that would be the radius of this semicircle. And we were told the diameter of our semicircle along the top was 4 feet, which means that this radius is 2 feet. And the height of this triangle, that is the distance from the top edge down to my slab, is what we were calling x feet. So this little third edge of my triangle is going to be half of that L of x function that I'm looking for. So let's think about visualizing this a little better. If we pull this triangle out, we have a hypotenuse of 2 feet, a height of x feet along this one edge, and then this bottom length along the last leg would be half of my L of x, length that I'm after. Now I can see that this is a right triangle, so using the Pythagorean theorem, I could solve for L. So let's take a look at it. We would have L over 2 squared plus x squared is equal to the hypotenuse squared, which would be 4. So squaring this, I have L squared over 4 plus x squared is 4. So L squared over 4 is equal to 4 minus x squared. So L squared is then 16 minus 4x squared. And so solving for L, we would have the square root of this 16 minus 4x squared, or if we factor out a 4, the square root of 4 would be 2 times the square root of 4 minus x squared. Okay. So finally, once I have the length along my slice there, or my slab, I'm ready to find its volume. So let's go up to the top here. The volume of this slice would be given by dV. So it would be found by taking the length of our slab, which is the same as the length of the trough or the tank, 8 feet, by its length, which was this L of x function, which we just found to be 2 times the square root of 4 minus x squared feet, by its height, which was dx feet. So simplifying a little bit, well, we have the 8 times twice this square root gives us 16, the square root of 4 minus x squared, times our dx, and this would then be in cubic feet. So once we have the volume to get the force needed to move this slab, or equivalently its weight, I would take the volume and multiply by weight density. So here the force needed to lift the slab, or lift the slice, is dF, which is found by taking my weight density, which was 62.4 pounds per cubic foot, and multiplying by our volume, which was 16 times the square root of 4 minus x squared dx, and this would then be measured in pounds, since we took pounds per cubic foot and multiplied by volume in cubic feet. So from force, we can find work by taking this force and multiplying by the distance that our slab has to travel, which is what we were calling x, the distance from the slice to the top edge of our tank. However, recall for this problem that we weren't just pumping our fluid to the top edge of the tank. We were pumping it through this spout, which had a height of 1 foot. So the total distance that this slab has to travel is x feet from the slab to the top edge of the tank, plus an additional 1 foot from the top edge of the tank to get through this spout. So I can say the work needed to lift this slice is dW, which would be found by taking the work that we found for our slice, or the force for this slice, which was 62.4 times 16 square root of 4 minus x squared dx, and then multiplying by the distance that our slab has to travel, which would be x plus 1 feet. I'm just going to put my dx on the end, and this is now measured in foot-pounds. So finally, to get the work for all of this fluid, which would be W, and I would integrate this differential of W. So of course I can pull the 62.4 out in front of the integral. I'm left with 16 times the square root of 4 minus x squared times x plus 1 dx. And let's think about where x, or what the range of x values is. So here x was the distance from the top edge of our tank downward. So since this was full of water, I would start with the water at the top edge of our tank, which would correspond to an x value of 0. And then I can go all the way down to the bottom of my tank, which would correspond to the radius of this semicircle. So here, since we had a diameter of 4 feet along the top, the radius or the depth of our tank would be 2 feet. So we could integrate here from 0 to 2. And this would be measured in foot-pounds. Okay. So here, again, we were just asked to set up this integral. We weren't asked to evaluate this integral. And in fact, thus far in the course, we don't have a technique for finding an antiderivative of that function. That's something that we'll start looking at a little bit more in our Chapter 3 materials, how to actually integrate this function. So let's consider one last example. Here we have a 10-foot long trough, which is filled with water. So 10-foot long tank or trough is filled with water, and the ends of this tank are shaped like inverted isosceles triangles, 3 feet tall and 6 feet across the top. So again, we're asked to set up an integral to find the work required to pump the water through a 3-foot spout on top of the tank, and we are asked not to evaluate that integral. So let's visualize this. We have a tank 10 feet long, and the ends are shaped like inverted isosceles triangles. So something like this, that are 3 feet tall and 6 feet across the top. And then the length of this tank here was 10 feet. And we were pumping the water through a 3-foot spout on top of the tank. Okay. So here, and we were told it was filled with water, so water goes all the way to the top edge of our tank here. So as we have with our previous examples, let's consider a slice or a slab of water within our tank. And here I'm going to let the depth or the height of that slab of water above the bottom of the tank be x feet. And I will let dx denote the thickness of that slice. So we can see from our figure that if I were to look at that slice, I would have a rectangular prism. And to find the volume of it, I would multiply its length by its width by its height. So of course, the slab is 10 feet long, the same as the length of our tank. It is dx feet deep, but I need to determine its length along this edge, which I'll call L of x. So how can I find L of x in terms of x? Well, again, I can make use of similar triangles. The triangle which forms, or the triangle which is formed by the edges of my tank and my slice, has the same angle measures as the triangle formed by the edges of our tank. So the ratio of the base and height to these triangles must be equal. So again, a little scratch work here, I might say using similar triangles, the ratio of the base to the height of the larger triangle, shown in blue, which would be 6 feet to 3 feet, must equal the ratio of the base to the height of our smaller triangle, shown in red, which would be L of x over x. So here it follows quickly that L of x is 6 over 3, or 2 times x. So once we have that length, we're ready to find the volume of this slice. So here the volume of our slice is dv, which would be its length, 10 feet, by its width, which we just calculated as 2x feet, by its height, which was dx feet. So altogether, 20x dx cubic feet. Now once I have the volume, I can multiply by weight density of water to get the force needed to lift this slice. So here, the force needed to lift this slice is, we'll call it dF, and it would be found by taking the weight density of water. So if we're measuring in feet, as with the last example, our weight density would be 62.4 pounds per cubic foot. And then we're multiplying by this 20x dx cubic feet. So let's see what we have here. We have this 62.4 times 20x dx, now measured in pounds. So to get work from force, we need to multiply by the distance that this slab is traveling. Now, if we let x denote the distance from the bottom of our tank upward, and the height of the tank was 3 feet, that means the distance from the top edge of our tank down to the slab would be 3 minus x feet. So this slab has to travel 3 minus x feet to get to the top edge of our tank. But recall it's then being moved through a 3-foot spout on top of the tank. So the total distance traveled will be the 3 minus x plus 3, or 6 minus x feet. So here the work needed to lift this slice would be given by dw, and it's found by taking our 62.4 times the 20x dx pounds and multiplying by the total distance traveled, which would be 6 minus x feet. And so this is now measured in foot-pounds. So the integral to get the total work required to pump all of this fluid through that spout is given by our 62.4 times the integral of the 20x times 6 minus x. So here, if I group these terms by distributing, I have 20x times 6, or 120x minus a 20x squared dx, still measured in foot-pounds. And let's think about where we're integrating over. So x, again, was the distance from the bottom of the tank upward. So for the water at the very bottom of the tank, x would be 0. And our tank was 3 feet tall. So to get the water at this top edge, we would have x equals 3. So here integrating from 0 to 3. So this integral would give us the total work required for pumping all of the fluid through that spout. Again, here we were told that we do not need to evaluate this integral.